All right, let's work an example. We're going to try to figure out the big O value for this function without actually trying to calculate the total number of steps that it's going to take. Okay, so we've got a function called work, takes in an array called nums. We're going to let n represent the number of data points in that array. Okay, so that's the length, is equal to the length of nums. Okay, make sure that that's clear. All right, so integer m equals the min value of integer. Okay, for int I equals 0, I less than nums.length. If nums bracket I is greater than m, then m is going to equal nums bracket I. Okay, so it looks like, what is this function doing? It's gonna keep searching and changing m as it gets bigger and bigger values of I. Looks like it's gonna find the biggest value in nums, right? It's gonna find the biggest value. So we have a loop. We're going to loop through all of the values of nums. So if there are, say, 100, if n is equal to 100, we're roughly going to have to do about 100 different calculations. Yeah, well, a little bit more that I equals 0, and then the n, maybe it's like 3n. Maybe it'll be 300 calculations, but basically we have to loop through each one of those values one at a time. We have to look at the first value, then we have to look at the second value, the third, and each time we're going to hunt through it and make our computer look at each one of these things. When it's done looping through all of the array, all 100 values, it's done. If I change this to 200 into 200, well, it's going to take twice as long to loop through all that. Right? But it's going to be a linear rate of change, right? We have to go through each different value in. For each additional data point I add, that's just one more thing we have to look at. So I think if you're following along with me here, that we can agree that this function is, whatever its calculation time is, it's O of n. Okay, let's do another example. Okay, I've got a method called put, which again takes in an array called R. We're going to let n represent the length of the array R. Okay, so we see a loop within a loop. So we're immediately expecting there to be something greater than ON. To really be able to get a good feeling of the big O function for an algorithm, you need to kind of understand what it's doing. So let's take a look at what this is doing. We're going to start at I equals 1 and go through the length. Okay, so we're not actually going through the entire array because we're not starting at 0. But if you have 1,000,000 items in your array and you start at the first, so you go through 999,999 items, basically you're going through n items. So we're seeing that there's going to be going through about n items here. Okay, but we're going to start with the k value equal to our I value. We'll say while k is greater than 0 and the array's kth value is less than the value before it. Now we started with k equals I and I starts at 1. So that's important. If we had started with I equals 0, this would be a problem right here. It could go out of bounds. Well, it looks like we're going to store it and then into a temp, and we're going to swap them. So we're swapping and moving backwards. Okay, so this is kind of like a modified insertion sort. It's a little bit slow on by swapping here, if you know what that is, but we'll discuss that much later. All right, so let's think about the best case scenario here. What's the fastest this could run? Well, this stuff here that's happening is only going to happen while k is greater than 0 and the kth value in the array is less than the value before it. So if I have an array R that's 1, 2, 3, 4, etc., all the way to some nth number n. Well, we're going to loop through here. First, I'm going to let I be 2, and k will equal I, and I'm going to look at that, and I'm going to say, R bracket k, the kth value here of 2 is not less than the k minus 1, right? So that's k, and that's k minus 1. And because it's not, we're not going to enter the while loop. All right, well then we're going to move forward with our I to a 2. And so now this will be k, and this will be k minus 1. And you can see, yet again, R bracket k is not less than R bracket k minus 1, so we're not going to enter the while loop. So what's going to happen is you're never going to do this code in the middle here. So there's actually a best case scenario here of ON. Because it's just going to loop through each one and say, no, don't need to do anything, don't need to do anything, don't need to do anything. But what if we had the exact kind of opposite? We had something like, we started at n, which, we'll say like n was like 100, and then we went down to 99, and then we went down to 98, 97, etc. Well, then what's going to happen is, the first time we come to this while loop, we're going to say, oh, I got to swap these two. Then we're going to come to this 98, and we're going to say, oh, I got to swap these two on the next iteration. And the 98 will move here, so we have 99, 98, and 100. But remember, we're doing k minus minus here, so after we swap one, we go down and we swap again. So we end up with 98, 99, 100. So what happens is that every single time, since these numbers are descending, every single time I come to, when my k is over here, I'm going to have to bubble down, just trickle that number down over and over and over again. All right? So the first time through, we're only going to have to, the while loop's only going to move a step, but as we go, the last time through, it's going to go through the entire thing, right? So on average, this while loop is probably going to, I think we could say on average, this is going to take about n over 2 steps. And if we multiply, I say n over 2 because, the first few times it doesn't have to trickle much. The last time it has to trickle the entire length of R, so on average, half of the length. But when you take that n over 2 and multiply it by the fact that we're looping through this entire array in the for loop, so we're going to do this n over 2, we're going to be doing that n times, right? So we need to say n times n over 2. Which is n squared over 2. But what's the big O for n squared over 2? Just n squared. Because typically, we don't need constants in big O because we have that n value that determines it for us. All right, so what does that mean? Well, we have a best case ON, and we have a worst case ON squared. And with a little more thinking, we could come up with an average case that's also ON squared. And so when we analyze algorithms, we're often going to talk about that. We're often going to talk about what is the best and worst case big O function for this algorithm. And at times, there's quite a difference. In fact, sometimes there's tremendous difference in the two functions. So, and this is certainly an example of it. All right, the last example I would like to talk about is kind of a cautionary tale. You see, when you come up with the big O function, it really helps to know what the functions do, what the algorithm is doing. If possible, you can actually calculate the t of n. But most important to remember is big O is not simply multiplying loops. So somebody might see this and say, okay, there's a loop. All right, that's going to be n. Here's another loop inside that loop, so it's going to be, since there's a loop in a loop, that's going to be n squared. Well, that's not true in this case. You know, that little shortcut when you see a loop within a loop, no, that doesn't always help. That doesn't always pan out. It is true that the first loop is going to have to iterate from I equals 0 through the length, changing by 1. That's going to be n. So we're going to do all this stuff inside here. That should be a 0 right there. I'm sure. I guess I erased it on accident. There they are. Okay. Now, all this stuff in the middle here, though, we need to figure out what's happening here. Well, that's just a 1, and you know we've seen how that doesn't really change anything. But what's happening in this loop here is that we're creating a k that's going to start at our I value, and then it's going to continue while k is greater than 0, so we must be doing some sort of counting down. But this is k divide equals 2. So let's take a look at what happens. So if I have an array, and I am at, say, this 8th value, okay? So let's say whatever, we're in the index 8. So that's going to be when I is equal to 8. When I is equal to 8, then that's where k is going to start. K is going to start at 8. And we're going to add the kth value of the array to some counting variable val, which we then later restore back into the ith position. So we're going to start there, but then after we add that value, we're going to divide k by 2. This slash equals means divide k by 2 and then change k at the new value. So 8 divided by 2 is 4, so k is going to come down here to 4. Oh, looks like I'm missing a spot here. 0, 1, 2, 3, 4. All right. Then we're going to divide, we're going to do some work, we're going to add, and we're going to divide 4 by 2 and get 2. And then we're going to, again add, and then we're going to divide 2 by 2 and get 1. And then we're going to divide 1 by 2, and since it's inner division, we will get 0. K is not greater than 0, 0 is not greater than 0, so that's going to stop right there. And pretty much the same thing's going to happen, when I is equal to 9, 9 divided by 2 is going to be 4, and then it'll resolve to 2, and then 1, and then with 10, it'll be 5, and then 2, and then 1. So basically, not a whole lot of change is going to happen. And in fact, it's not even going to be till we're up to 16. When we finally get to 16, 16 divided by 2 is 8. So, and then 8 divided by 2 is 4. Well, when K started at 8, we did how many calculations? We certainly didn't do 8 of them. We did 1, 2, 3, 4. It's not going to be until we get to 16 that we'll have 5. Or probably it'll be, depending on the math, it might be somewhere between there. But when we get to 16, we'll still be at 5. And then, I think you can imagine it'll be out till 32. Then we get that 6th one. And that's because it's doubling in how long it takes us to actually do more work. So if K started at, say, 64, we could figure that out. We could say, well, 2 to what power is 64? Well, that's 2 to the 6th, right? Or in other words, we could say that the log base 2 of 64 is 6. So to calculate how many steps this is going to take, it actually depends on the log of this kth value. So we're not doing in steps here. We're doing the log base 2. And since all the logs are kind of in the same family when you multiply them by something, what we ended up doing is ignoring the base 2, even though quite often in our program analysis it will be a log base 2 situation. We're just going to call this log of n. So we're doing log of n steps in times. So we're going to make the assertion that this algorithm is O n log n. Big difference. Big difference between n squared and n log n. And we're going to see that come up a lot when we talk about sorting algorithms. So be careful. Think about what's happening. Check how these variables are changing to make sure that you avoid the pitfall of just thinking you multiply n squared when it's a loop within a loop. Not always the case. All right, well, do some practice problems. Good luck.